Hello, welcome back to the channel. So let's continue our previous video and check whether this definite integral over here converges or diverges based on the comparison test that we covered in the last video. So if you have not watched my video on comparison test, I'll highly suggest you to first watch my video on comparison test before going over this solution over here. And the basic overview about the comparison test is, we know that in comparison test, basically we'll compare our definite integral function with another function. And for the another function, your another function should always satisfy this first criteria over here, which is that your g of x, the second function, should always be greater than or equal to 0 for all the values of x which lie in the interval of the definite integral specified. So in this case, since the definite integral is from x equals 1 to x equals infinity, while choosing our second function, we should choose our second function to be the one which is always positive for all the values of x greater than or equal to 1, right? So that is the first case, and also a very important point about the second function that you will use in order to compare it with the first function is that you should definitely know whether your second function integral for the same interval converges or diverges. So it is always better to assume your second function to be the one for which you already know the definite integral for. So since in this case, we are not familiar with the integral of e to the power minus x square, right? This is a very famous integral, by the way, but we don't have a general method to solve this definite integral over here, right? So what we can do is we can use comparison test to check whether this definite integral converges or diverges. But now we need a second function to compare it with, right? So we know that since our first function, the function for which we are calculating the definite integral for, is e to the power minus x square, and now we want a second function g of x, which is always greater than or equal to 0 for all x greater than or equal to 1, right? So we want our second function to be the one which is always greater than or equal to 0 for all the values of x specified in the original definite integral, right? And since we also covered one more important point about g of x, that we should also know the definite integral solution to the second function integral, right? And one function that we can think of is e to the power minus x in comparison to e to the power minus x square, right? We definitely know the integral for e to the power minus x, and e to the power minus x, since it's an exponential function, it's always greater than or equal to 0 for all real values of x, right? So since here we are only concerned with all the values of x greater than or equal to 1, we know that our exponential function is always positive. So now we satisfy both of the criteria of our second function. Our g of x is a function which is always greater than or equal to 0 for all values of x greater than or equal to 1. And we also know a definite integral solution to this function over here, right? And now based on the comparison of both of these functions, we can clearly notice that for all the values of x greater than or equal to 1, so for all the positive values of x greater than or equal to 1, this e to the power minus x square is always less than or equal to this function over here, right? And the reason why we know that is because on the left hand side you can see that you have e to the power minus x square, which can be written as 1 upon e to the power x square, and on the right hand side you have 1 upon e to the power x, right? And since you know that for all values of x greater than or equal to 1, e to the power x square is a faster increasing function than e to the power x, right? Because it has an x square term in the exponent. So since this function is a faster increasing function than this function, then you can clearly state that the reciprocals of these two functions will have inverted inequalities, right? So that is why we know that our function for which we are calculating the definite integral for is always less than equal to our second function. So now based on this property, we can clearly use the case 1 over here, right? We know that the function for which we are calculating the integral for, the absolute value of the function, so in this case, since we have an exponential function, the absolute value of the exponential function doesn't matter, right? Because we know that our exponential functions are always positive. But we do satisfy the case 1 over here, right? For our f of x, which is e to the power minus x square, we know that the absolute value of e to the power minus x square is always less than or equal to e to the power minus x for all the values of x greater than or equal to 1 over here, right? So now let's calculate this definite integral over here, because if this integral converges, we can clearly state that our original definite integral will always converge. So now, since we are concerned with the integral from a to infinity of g of x dx, which in this case is simply 1 to infinity g of x is e to the power minus x dx, and in order to solve this definite integral, we'll use all the concepts that we covered in the last video. So what we do is basically we take limit r approaches to infinity for 1 to r e to the power minus x dx over here, right? And now we can solve this easily. We know that the integral of e to the power minus x is basically e to the power minus x upon minus 1 with the endpoints 1 and r. We can take the minus 1 out. We can take this minus 1 out to avoid any confusion. So if we take this minus 1 out, this would basically be limit r approaches to infinity e to the power minus x with the endpoints r and 1. And now this would be limit r approaches to infinity. The inner expression will be simply e to the power minus r minus e to the power minus 1 over here, right? And you know that when you'll take limit r approaches to infinity, this term approaches 0, right? Because this is 1 upon e to the power r. So if capital R approaches infinity, this expression approaches 0, right? So this expression over here will be simply equal to minus e to the power minus 1, right? So this will be minus 1 times simply minus e to the power minus 1. And this would be e to the power minus 1, which is 1 by e. So now we know that if we solve this definite integral over here, the definite integral of this expression, the definite integral for our second function, we can clearly see that our definite integral has a real solution to it, right? So we know that this integral, our g of x dx integral converges. And now based on the first property, based on the first case, we know that we satisfy this criteria clearly, and also we know that the integral where our gx is e to the power minus x, since we know that integral has a real solution to it, so we can definitely argue that our original definite integral, which is this one, will also converge. So now based on the comparison test of this definite integral with this definite integral, we can clearly argue that this definite integral also converges. So that's it for this video. Again, the main takeaway from this video is that whenever you're choosing your second function for which you're comparing your first function with, always choose the second function to be the one which satisfies all the criteria that we discussed in this video. So feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.